Welcome back. So let's try and refine or revise our hash function from the last video just a little bit. So it's still not going to be revolutionary. It's not going to, blow the minds of computer scientists around the world. It's going to be pretty bad, but it's at least a little better than what we had in the last video. So we're going to focus on improving its performance a little bit so that it runs closer to constant time. And then also we're going to try and increase the randomness, the distribution of things throughout our buckets in our hash table. So here's the code. This was the original one that we had. And the first thing we'll do to make it a little bit faster, so if our key length if our key approaches like 200 characters or 500 characters, although there is a maximum length to a string, but let's just ignore that and say as our key becomes 1,000,000 characters, we're not going to loop over every single character. All that we'll do is add in a minimum. So we're going to take math.min between the length of the key and 100. So whichever one of those is smaller is what we're going to actually loop. So if our key is 30 characters, then we're going to just loop 30 times. But if our key is 1,000,000 characters, we'll just do the first 100. So this is not a perfect solution, but this will work for us for now just as a slight improvement. And it's really, honestly, the reason I even put this here because we're not going to work with any characters or any strings that are greater than 100 characters anyway. I just included this to really hit on the point that you want your hash function to be as fast as possible. But we're going to work with small strings that are like 10 characters anyway, so this doesn't honestly matter. Now, the second thing that we're going to do is add in prime numbers. So I'm not going to go into a ton of math here because, frankly, I don't understand half of it. There's a lot of, I actually asked one of my friends, this is a math PhD, and I talked to him about this, and he wasn't totally clear on exactly how it works either, but hash functions almost always take advantage of prime numbers. And there's a couple reasons, but it comes down to reducing collisions, meaning that we don't want data to be stored in the same buckets if we can avoid it. We want to make sure that we are spreading data out as much as possible so that it's faster to retrieve. So anyway, I'm not going to go into a ton of detail or really any detail because it's complicated, but just know that prime numbers, when you use them, especially at the end, if the length of your table itself, the array that you're storing data in, is a prime number, like 31 items long or 13 items long, generally the larger the better, the less likely it is for you to have collisions. And just to illustrate this point, did a little research. There's this question on Quora that has a really good answer. There's a lot of really bad answers to this question on Stack Overflow. People don't really explain it. But this, apparently it's from some guest lecture at MIT a while back. And this person ran a little experiment where they hashed 10 million pairs of data, key value pairs, using different hash functions in different sizes of the actual list or the table they stored it in. Some of them were prime and some of them were not. And you can see, let's just take a look at these first two hash functions. For 10 million pairs of data, this is it's called the search cost, basically the measurement of how many collisions there were. So if we take a look, between a prime number, 8191, that's a prime number, 1.92 collisions. Now if we look over here, we use an even number now. Look at all these collisions. This is bad. We don't want more collisions. So just using a different table length, just one number smaller to make it prime, led to a huge, multiple orders of magnitude decrease in the number of collisions. So this is much, much better here. Or the same thing with this, a different hash function. We have 90 is our measurement of the collisions. I don't really know how it's established what 90 actually means, but we can compare that to 4,196 collisions when we use a non-prime length for our list. So the hash table that we're storing things in, it's always good to make it prime. Even if we don't go into a ton of detail on exactly why, you can see here just from this table, changing a prime number, so it's just one number smaller, but a prime number length of the table versus an even number, huge increase or decrease, depending on how you look at it, in the number of collisions. So we're going to use a prime number for our length. Okay, so here's our new hash function where we have our key and our array length. This time we should use an array length that is prime. So let's try hashing, hello, and using 13, and we get 7. Let's try doing goodbye with 13, we get 9. Let's try hi, 10. Cyan, we get 5. Okay, so we're not really going to be able to see if our distribution's any better. It's such a small data set right now, and the length is only 13. You want to use a larger prime number ideally, but we're also only storing trivial pieces of data because this is just a learning exercise, so it doesn't honestly matter. But the improvements we made, in principle at least, are to speed this up so that we set a maximum. We're only going to loop at most 100 characters. So if you pass in a huge piece of data, we're just going to look at the first 100. And if at that point, if we have two strings or two pieces of data that are identical for the first 100 characters, that's okay. They'll collide. We'll store them in the same place. If you know that all of your data follows that pattern, like you're storing 1,000 character strings and the first 100 is always the same, and it was the last couple that were different, well, then we'd probably tweak our algorithm to start at the end of the string, for example, or we'd do something. But just for this sort of all-purpose example, we're going to cut it off at 100 characters, really just to show you that you should consider that, even if it's not practical for us. Then also, we're adding in a prime number, and we want our array length to be a prime number as well, just to decrease the number of collisions, to make our data more distributed, more random, even though random's not really the correct term because prime numbers aren't actually truly random in their distribution. Not my wheelhouse at all. But anyway, whether this is a great hash function or not, and it's definitely not, it still works well enough for us to implement a basic hash table. So that's what we're going to work towards next. What we have to talk about first is how we handle collisions, because we will, let's see if I can reproduce one. Let's try doing like, what does pink give us? Poink. Okay, that gives us 5 as well. So what happens when cyan and pink have the same index? What do? Do we store them both there? Do we make the list longer? How do we handle it? That's what we'll talk about in the next video. There are 2 solutions, and then we'll actually go and implement one of them, create a full hash table. So that's coming up next. This is our basic hash function, only works for strings. We improved it a little bit. It's sort of constant time, and also we added prime numbers in so that it's slightly better distributed. Okay,